Everyone, in today's lecture we're gonna start discussing the stack in AVR. How do we access it, how do we get stuff into it, and what is it exactly. So a stack is actually a data structure found in SRAM. So as you know, the memory is divided into 3 or more parts. This will be the GPR, this will be the SFR, and this is the SRAM. So actually, the stack is found at the bottom of the SRAM. So stack is found or created at the bottom of SRAM. So if you have an Atmega 328, you have 16 bits for address bus. This is 16 bits. However, the last location, since we're not gonna use all the 16 bits, the last location in SRAM is 0x85F. So this location is 0x85F, and this is the starting place of the stack. Okay, so this is where the stack. So what's a stack? Stack is a data structure to save data. Its primary usage is saving data for later use. Okay, so data, this could be registers or call addresses. And we're gonna talk about call addresses in a little bit. So let's say I only have, as we said, we have only 32 registers. So let's say I want to have to save this register for, probably because I don't have enough registers. So let's talk about one. So saving registers. For this I have two instructions, push and pop, and both of them take a register. So when I say, let's say LDI R16 0x25 push R16, so what happens is that this is the SRAM. We will have 0x25 here, and then the stack pointer, which I'm going to discuss later, will point to the next empty place. So we just place 0x25. This is not very clear. Use a different pen. So this is 0x25. Okay, so having 0x25 here is just saving it for later use. So let's say I want to pop it back. So I say pop R17. So it would look, what's the last location? It's going to have 0x25. So what's happened is that R17 now will be equal to 0x25. So a stack is a place for saving data. Okay, so this is what we need to know. So let me reiterate. So we have the stack here, like this. It's an empty stack. Okay, so this is 0x085F, and this is a stack pointer. So SP is a 16-bit special function register that points to an empty location in stack. So this is 16 bits because it's pointing to an address in SRAM. Okay, and the stack pointer, okay, this is stack pointer. So what happens on a push? Let me repeat the example. And then we say, okay, push R16. So what happened first, it's gonna go to stack at SP, and it's going to say, okay, this should be equal to 0x25, and then it's going to subtract 1 from the stack. So SP is equal SP minus 1, because it's going to go to the next empty place. So first it's going to place 0x25, and then the SP will be pointing here, which is 0x085E. Okay, so it'll be subtracted. So initially we must point SP to be equal 0x085F, which is the top of the stack. Or TOS. Okay, so now after a push, this will save the value in SP and it's subtracted to 1. So here, after this operation, SP will be equal to 0x085E. If we do another one, let's say I'm gonna do LDI R17 0x30 and push R17. So what happened is 0x30 will be here, and of course SP will be subtracted to point to the next empty slot, which is 0x085E. Okay, so always the top of the stack is pointing to the next empty location. So this, it points to the next empty location. So now using pop, okay, so let's say first I'm gonna try pop R20. You can use any register. So what happens first is that we check what's in the stack. In the stack there is 0x30 at 85E and 0x25 at 85F. At 85, this is D. So at 85D, what we have is empty, and here what is the stack pointer pointing to. So first I'm gonna do SP, I'm gonna increase SP plus 1. Now I'm at 0x85E. 2, I'm gonna say R20 is equal to 0x30. Now the stack is going to look like this. It's gonna have 0x25, and the stack pointer is going to look like this, and this is 0x085E and 0x085F. Now if I do another pop, let's say R21, so first I'm gonna have SP is equal to SP plus 1. This makes SP is equal to 0x085F. I'm gonna add 1, and 2, I'm going to say R21 is equal to 0x25. Now what happens if I do a third pop? Let's say R22, I can use the same register. It's going to generate a stack underflow. Why? Because it will try to do SP is equal SP plus 1, and this will be 0x085F plus 1, which is undefined. So it will generate a stack underflow. So first, before actually using the stack pointer, something that's very important is that we need to initialize the stack pointer. So the way we do it is, there are two ways. First method, we say LDI R16, okay, 0x5F to out. This should be, remember, SP is a stack pointer. The 16-bit register is divided into two SFRs, okay, SPL and SP high, stack pointer low byte, stack pointer high byte. So we need to put the low byte in SPL. So SPL R16, and 2, we need, well, it's the first method, LDI R 17 0x08 out SPH R17. The second method is using RAM end. So what we do is we say LDI, same thing, R16. If we don't know the exact address, we can say low RAM end, since here we don't need to actually know what's RAM end. RAM end in our case is 0x085F, and then again out SPL R16, and we can do LDI R17 high RAM end, and we say out SPH R17. So in this case, of course, RAM end is equal 0x85F. So whenever we want to use the stack pointer, we need to initialize it accordingly. I'm going to use the second method. It doesn't matter which method you will use. Now this is the first usage of stack. So now the second use of a stack is for functions. So what are functions in AVR? Functions are very useful in coding to organize our code. So assume I have a delay function. I don't want to place it inside my code, I want to place it outside my code. So the way I do it is with two instructions. One is call, okay, call, say delay or any label, for example, could be any label, and 2 is going to be return. So call is a 32-bit instruction. Okay, remember this. So let's say I start my program with LDI R16, 0x25. Then after a while, I want to call my delay function. Then I have another instruction under it, LDI, let's say R17, 0x30. Then I go to delay. It can be anywhere. Let's say origin 0x300, and then my delay will have some instructions and then a return. Okay, so let's say the address of this instruction is 0x0005. the address of the next instruction will be 0x0007 because call is a 4-byte instruction. Okay, so the way the code works is as follows. So first of all, I start executing those instructions, and after I reach call, I jump all the way to the delay, continue executing my instruction. When I hit return, return is my way back to the instruction just under the call, because if I return to the call, it is going to have an infinite loop. So I return just under the call delay instruction at address 0x007. So a call function differentiates from a jump instruction is that it saves the return address. So call goes jumps to delay, and when a return instruction is encountered, it places the PC and the instruction directly under the call. So let's write this. So first, a call label. What it does is jump to label first, and then what happens is that it will push on the stack the value of PC. Let's say this is PC is pointing here, plus 2. Okay, in our case it's going to be PC plus 2 is going to be 0x0007. Okay, so if we take a look at the stack after properly initializing the stack pointer, we put the higher byte at the last entry. So this is 0x085f, 0x085e. So we place here 0x00 and 0x07. So we place the high byte first, and then low byte of what? Of PC plus 2, okay, which is 0x007. Now, when a return instruction is encountered, it's going to go ahead and look for the stack, checks that the return address is 0x07. So on a return, what happens is that it pops the stack. Let me write it down here. So on a return, first it pops the stack into PC. This means it will place PC is equal 0x0007. Okay, and take everything out of the stack, and this will make the jump to 0x07, and I can continue my execution as before. Okay, so let's take a more complicated example. So write a program to count from 0x00 to 0xFF and send the count to port B. Use a call subroutine for sending data and another for delay. So let's define some variables. So I'm going to say define count equal R20. I'm going to start from 0. Okay, so first I need to initialize my stack pointer. So I'm going to use the RAM at the high RAM end. And then I'm going to place this in SPH. Then I'm going to LDI R17 low RAM end, and I'm going to place this also in SP low R17. This is just SPH. Okay, and then I'm gonna initialize my counter. to 0, and I'm gonna do infinite loop that will call display and R jump back. Okay, then in display capital D, what I'm gonna do is the following. So first I'm gonna increment my counter. Second, I'm gonna place it on port B, out port B, comma count. This is the value I want to place. I'm gonna call delay. And then I'm gonna use a return. Okay, then let's place the return in 0x300. I'm gonna say, okay, delay will be LDI. It's a typical way to do a delay. So we're gonna loop for 256 times, and I'm gonna do again, and then again I'm gonna place 3 knobs, and then decrement R16, branch not equal again, and then I'm gonna do a return. So this is a simple problem. So the first thing I need to do is start with writing the addresses. So first, because what I'm asking here is, what I'll be asking is, what's in the stack after each call. So we start with, this will be 0x0000. Notice that defining count and origin does not take any place in program memory because they are not actually instruction. This is 2 bytes. Okay, then 2, 3, 4. Okay, this will be 5. This will be 0x 6. No, actually a call takes 2, so this will be 7. Okay. Okay. 0, 1, 2, 3, 4 is an LDI count, 5 will be the call, and 7 will be yes. Now after the R jump takes 2, so this will be 8, and then 0x0009, then 0x000A, and 0x000B. Now these instructions will be as follows. This will be 0x, of course origin does not take anything, and 301, 302, 303, 304, 5 branch take only, also 2 bytes, 306. Now that we place all the addresses, we can discuss what is inside the stack. So I'm gonna ask you what's inside the stack at this point. So after I go to the first instruction, so this is the first call, okay? So at this point, after the call, what is inside the stack? So call display, so the stack is as follows. Of course, the stack will have the return address after the call, which is going to be 0x0007. So this will be 0x00x07, and the stack pointer will be here. Okay, so PC will be equal to display. So I'm gonna go to display. Okay, the stack will be as follows, and the stack pointer will point to 0x085D because this is 0x085F, 0x085E, and 0x085D. Okay, now the second question will be, so after going, I will be going directly to here, and then I'm gonna go inside the display. There is a call delay. So after the call delay, what's in the stack? So to call delay. So this is this point. Okay. So what happens is that I'm gonna place inside the stack, we already have 0x00, 0x07. So at the empty places, I'm gonna save the return address, which is 0x000B. So this will be 0x0B, and the stack pointer will be here. So now this is 0x085F, this will be E, this will be D and C, and finally we will have B. Okay, so 0x085B. So PC will be equal, after calling call delay, the PC will be at 0x0300. The SP will be at 0x085B, and the stack will have, this is the address of call that resulted from call display, and this results from call delay. Now, after I go to call delay, I'm gonna do my delay, and I'm gonna hit the first return. I'm gonna do the different color. So this is the first return, and this is the second return. So at the first return, okay, first return, what will happen is that I will place inside PC the address at the top of the stack, which is the address will be, it will be 0B. So the first one will make PC is equal 0x000B, and the stack now has only, and here's the SP. Okay. Okay, so the PC will be like this, the SP will be equal 0x085D. At the second return, the stack will be, as for PC, will be 0x0007, and the stack will be empty because I popped the last address. So as we see, the first call plays 07. These are called nested calls, call inside a call. Okay, if we had multiple calls that are not nested, it will not increase the stack values, because we need to have stacked calls in order to add, to increase the stack. In our case here, we had a call, a function inside a function. So inside the display function we had call delay, and this will actually have what will add to the address of the stack. So now to better illustrate this idea, so imagine I have at address 0x00 0A, I have call, say delay, and then later I have call, let's say output. It's at 0x00, let's say 10. So initially what will happen here is that this will go to the call, to the delay, and I have a return, and this will go to the output, and I have another return. So the stack will be as follows. After the first call, say this is the first call, this is the second call. After the first call, I'm going to have 0x00, 0a, 0a. I'm going to return. So this is call. Directly I have a return. So this will be empty again. This is after 1. Now at 2, the stack is empty. So I'm going to place 0x00, 0x. Well, actually, this is not A. This should be A, B, C. This should be C. Okay? And this 0x is going to be 1, 2. Okay? And then after the return, it will be empty. So the difference between the previous example and this example is that these calls are not nested. We don't have a call here for the stack to increase. There is no nested calls. One final note is that as with jump and rjump, let me start on a different page. As with jump, it is 4 bytes, and rjump, just 2 bytes. We have call, which is also 4 bytes, and rcall, which is 2 bytes. If I'm going to look at the way call is, it's actually similar to jump. I have K20, K19, K18, K17, and then I have 111, K16, and then I have K15 all the way to K0. So this is the layout for call instruction. So when I want to push, I will push PC plus 2. However, with rcall, it's just 2 bytes. So when I want to push, inside for rcall, it's going to be PC plus 1. For example, if I have rcall delay, and delay is here, this is 0x0000A. So what will happen is that I'm going to push on the stack 0x00 and 0x0b in case it's an rcall. If we have call delay at 0x000A, and then we have the delay here, then on the stack there will be 0x00, 0x0C. So we notice here this only takes one location. So here if you have an LDI, it will be at 0x000B, and if I have an LDI here, it's going to be at 0x000C. So this is the main difference. Otherwise, similar functionality. Of course, rcall is faster. It only takes 2 bytes. It makes your code closer, but it has a limited range. Call can go all over the program memory. And this finalizes the lecture on stacks.